So, welcome everyone to the current lecture of field extension. So, today we will talk some important results and definitions of field extension. First of all, let me define what is finitely generated extension. Okay. So, it is finitely generated means F is a space, F is a field, K over F is an extension. So adjoin finitely many elements. Then it is called finitely generated field extension. First of all, you all know that for one element, if I attach one element to FA, K is field extension over F, then that is called simple extension, you know. So that means we are attaching more elements to the simple extension and making the field bigger. Okay. So this is the main concept of finitely generated extension. So let me write out first the definition. Let F a field extension A over F is called finitely generated. There exist finitely many elements suppose I name them as alpha 1 to alpha n. Finitely many element such that k equal to this. So in other words, in other words, k is obtained from F by attaching finite number of elements. So that elements must belongs to K. Okay. They are all elements of K. Element and at each step take the field. Hence, as ring and in each step take the field. For example, what I am trying to say, that is, you are given F, first attach alpha 1 and you get the polynomial ring. Okay. Now take this, which is the quotient F alpha by G alpha, where G alpha is non-zero. Okay. Then do one thing. Then on this thing take alpha 2. Then it is a polynomial. Now take the quotient of polynomial. You will get this thing. And at the each step, at the last step, you will get this thing. That is K. Okay. So you might be confusing with two terms. One term is finite extension. Finite extension and is finitely generated. Two things are different. Why they are different? Finite extension means if the vector space dimension of this is finite. And this means finitely generated means if K can be obtained by attaching a finite number of elements. So observe that finitely generated extension need not be finite. Why? Take Q pi over Q. So this is finitely generated extension. In fact, simple extension. Only one element. But it is not finite. Because there are vector space dimension is, if you consider, there will be 1 pi, pi square, everything will be there. Okay. Now, I told you a process first from F1 alpha, then consider this. Then if you take the quotient, then you will get F alpha 1, alpha 2. But does it equal to this? So if this is equal to this, then we are getting this. They might not be equal, they might be equal. In our next theorem, we are saying yes, they are equal. I mean, if you take the field first and then suppose this is f dashed, then f dashed at adjoint beta is actually f alpha comma beta. Suppose this is equivalent to saying if R is a ring, then Rxy is obtained by take the ring first Rx, then in this ring, over this ring take this. They are equal. So in the analogous to field theory, they are also equal. I mean, if you first take the field and taking the field as a coefficient over this field, take this extension. I mean, and you will get by getting this thing. So in Tower law, okay. Our next theorem, lemma f alpha comma beta is equal to f alpha over this thing, take beta. That means if I go through this thing, I mean, suppose this is f. So this is an field extension. F alpha. This is a field extension. Now over this extension, if you are taking f alpha over beta, this is a field. Now this is our f. My name is f dash. So this is a field. And if you take independently if you independently take another extension, that is simultaneously inputting two element, then they are equal. This theorem says that. I think you got that. You got it. So if we prove this, then inductively applying same thing, we can say that if alpha 1, alpha 2, alpha 3. This is same as first. If alpha 1, alpha 2, this alpha 3. I can inductively performing this and say this. Okay. How to prove this? Okay. So I need to set theoretic inclusion. Right? And the concept of smallest subfield. Okay. Remember, what is smallest subfield containing F and alpha? Smallest subfield. This is this thing. Okay. Now, consider F alpha, this thing over beta. This is the smallest subfield. This is the smallest subfield containing what? F alpha and beta. Now, if alpha comma beta is another smallest field, beta. Okay. Why? Because see, F alpha sits inside this. As you know that Rx contained in Rx comma Y. We are taking only the polynomials in X. Here only we are taking only the field elements of the quotient in alpha. So it is any field containing them, and it is the smallest. So this must be inside here because it is the smallest. So alpha F alpha thing beta. Okay. Again, we will use this condition. Also, observe that F alpha over this field, if we take beta, observe that contains F beta. And what is F? It is the smallest field by definition. Thus, we have Totally, the equality occurs. Okay. Hmm. Okay. So next thing is also important. It is interesting. For example, question. Suppose you are given finitely generated extension. If then what can you say? Degree of extension if you know degree of generated. So I want to ask, suppose you are given, for example, alpha 2, alpha 1, alpha 2, alpha 3, which is k over f. Now, suppose you know what is f alpha 1, f alpha 2 over f, the degree you know, and f alpha 3 over f, that you all know. So can you give me that, what can you say about the degree of extension k over f? I mean, the total degree. First of all, can you say something if you know individually? Or if you cannot give me the proper answer, can you tell me about some apart from that is important question of finitely generated extension. So it's not a question. I mean, suppose k is finitely generated extension. Okay. Suppose I have attached k element with k alpha. Alpha k belongs to the extension f, and and it is a finitely generated extension. And suppose assume that the individual is unknown. Okay. So what can we say about this? So observe that. So you use our previous tool to answer this question. Okay. First, let me assume f0 equal to f and f1 equal to fi. Okay. I mean, That means I am writing two steps, you will get it. What is F1? F1 is F0 alpha 1. If you put 0 here, F2, F1 alpha 1. But what is F1 alpha 1? F1 means F0 alpha 1. Sorry, it is alpha 2. Alpha 2. But we already know whatever we have shown here, it will be absorbed inside this. So that will be precisely equal to the alpha 1, so F0. That means it is F0 is F. So I mean, this way, inductively, you can get F I plus 1 is actually F adjoint I plus 1 generators. This is actually this thing, alpha 2. So consider the tower. What is the tower? It is called tower, okay? Sometimes they call tower of field extensions. First one comes F, then which is F0, then comes F1, then comes F2. It ends with where? Last time is Fk. So it is Fk, which is K. Okay. This is small k, this is large scale. And that doesn't matter seriously, to be honest. These two k are different. Now, this is a number and this is a field. So you can assume that is k. That is small k. Okay. So this is also small k. They are not same. Now consider, now take any middle thing. Take F I plus 1 over F5. That extension. That is F. But this is actually, what is this? This is actually this extension. Actually, what? If I take this field as F, then it is F alpha I plus 1 over F. Okay? This is this extension. Now we know I assumed there, right? So this extension of this degree extension of this degree extension degree of extension of this extension this depends on the minimal polynomial equal to degree of minimal polynomial of alpha I plus 1 over the field this thing. Okay. We know the that the degree of but what about what information we know about the minimal polynomial? We know that minimal polynomial of alpha plus 1 of this thing over f, sorry, alpha I plus 1 over f next is ni plus 1. So the coefficients are coming from, observe that the coefficients are coming from f. So I can treat is as the coefficients of the bigger field, this field. So what I get in this field, I have get this polynomial whose alpha I plus 1 is a root because it is a minimal polynomial, monic irreducible. So this thing will divide this thing because this is an arbitrary polynomial here. Okay. So where we were that this thing, I mean this polynomial, if you think carefully, the polynomial belongs to also here, I mean in if alpha 1 to alpha I x, I mean if you consider this thing, because it is a much bigger field, than this, so this thing. But what is actual minimal polynomial of alpha I plus 1? What is actual minimal polynomial over alpha I plus 1 over this field? Then we will divide this because this is any polynomial over this field. Understand? This is any polynomial, that is alpha I plus 1. Okay. This is any arbitrary polynomial as alpha I plus 1 over this field as alpha as minimal polynomial of alpha I plus 1 of this field is the monic irreducible polynomial having alpha I plus 1 as a root and M alpha I plus 1 over if smaller field if x is any other polynomial having alpha I plus 1, sorry, it's a root. So it is minimal polynomial will divide any polynomial having the same root. So so this thing will divide this thing. So over x right m of alpha I, sorry, alpha I plus 1, alpha I plus 1, the field f x. Fine. Therefore, what is degree of extension of alpha? So that means, what does that means? That is degree of, okay, let me write here, degree of that polynomial. So it divides means this polynomial has lesser degree of this polynomial. That is obviously smaller, less equals to equal might be happen, because if I get no other polynomial, then that polynomial might serve, because it is already present in also this thing. It is already present there. So if I cannot get any smaller polynomial, that is serve, and in that case the degree will be equal. So degree of n of alpha I plus 1 over f x, which is, what was this? It was, I think, and this degree, okay, imply that, but this is what? This is actually this thing. This is and this we assume that ni. Okay. Sorry, it is alpha I plus 1. This is alpha I plus 1 colon f. So what if we apply this thing? If we apply this thing at each step, then I will get this degree is less than n1. This is actually equal to, I think, because it is f. So this is equal to n1 over this. This is less than equal to n2 over this. This is less than equal to n3 dot dot dot. This is less than equal to nk. So if we multiply this, because the degree is multiplicative, so I am explaining another thing. What is this? K colon f. This is nothing but f adjoint alpha 1 alpha I plus 1. So this is k means alpha k, I think, right? We attached k elements. Yes. So we attached k elements, right? But observe that this is by Tower law, it is product of intermediate fields. K minus 1 is, sorry, this is just one less product. Small k. This way I will get the product will give last the and last thing. But we showed that in that there. So if we put I equal to k minus 1, then I will get this thing. Okay. So in this is less than nk, because I plus 1 will be k minus 1 plus 1, small k, this k. So it is nk. This extension, the degree of this extension will be less than n of k minus 1, dot dot dot. It will come increasingly, decreasingly according to index of n. It will be there alpha, sorry, n2, and it is equal to n1. That is less equals to n2. That also less equals to, okay. So into dot dot dot. So that is the field extension. So what the information we can get? We can get, if we know degree of alpha over f, that is the degree of minimal polynomial over f, then if we get this degree of minimal polynomial, then I can get an upper bound. When the equality holds, it is an inequality. When the degree are equal, that means the minimal polynomial divide, but if it is actually equal, the degree will not change. When minimal polynomial of alpha I plus 1 over f alpha I, this is actually equal to minimal polynomial of alpha I plus 1. That is in the variable x, okay. I equal to 0 to k minus 1. Then you will not, then the degree will be exactly same of the base degree. Okay. Now the question is, how does an element look like? How does the element come? That is another question you can possess. So to answer the question, remember that what is the element of f alpha equal to, that is some polynomial in alpha, a0 plus a alpha n minus 1, where a0 dot 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 an minus, and the degree of extension, that is the minimal polynomial degree of alpha about f equal to f. Okay, we know this is a formula. We'll use this inductively to get this. For example, let us in particular find the orbiter. Okay, so in particular, I mean, if I can do this, you can inductively. So, what is f alpha 1? An element of f adjoint alpha 1, alpha 2, alpha 3. So then you can apply. Then you in this way, if anybody asks you what is this, so once we do this, we can write it at alpha 3. Okay, so inductively you can do this. Then what is this? Oh, so we need information about beta for this thing. We need information about beta. Okay. So for this, suppose this is, you can assume that as okay. You can assume this as a D. If we assume, I mean, if we assume this, take x belongs to f of alpha comma beta. Now, f of alpha comma beta is actually f of alpha on this beta. Now, if we apply this formula, in place of f, put f, in place of f, you can put f alpha, and in place of alpha, if you put beta, then it will be a polynomial of in beta of degree d, right? Because the degree of extension is d, and we are about to find out the minimal polynomial over f alpha. Okay. That means x equal to some b0 plus b1 beta plus b2 beta plus b b minus 1, sorry, it is beta squared, beta g minus 1, where on which field we are inquiring? On f alpha. So the coefficients will be on f alpha. B0 dot 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 B Now observe that. Now take any BI. Now take any BI from this set. Zero. I to I 0 I B minus 1. Now BI, we are again applying this on. So BI belongs to FA. Now FA will look like this FA will look like this form. So each BI is expressible in this form. Then BI, for BI I am writing, suppose A0I plus A1I alpha plus A. So it is degree of extension is n. So n minus 1 will be n minus 1 comma I. P0 comma I, 1 comma I. It will be alpha to the power n minus 1. Where? On which field I am taking? I am now BI belongs to F alpha. And F alpha on F we are taking. So the coefficients will must come from F. Where? Where? B. Where? A 0 comma I dot dot dot. What is the last element? A n comma 1 minus I, that belongs to F. So if I put the value of BI, what will, so it is for BI, take any BI, okay? Any. So B0 is expressible in this form, B1 is expressible in this form, B2 is expressible in this form, D minus 1 is also expressible in this form. So if we put the values and do putting values of BI in the above expression, what we would get? We would get x equal to, we get, what we are getting, x equal to, so B0 means A00, A00 plus, we are putting 0 here. So A1 comma 0 alpha plus A2 comma 0 alpha square plus, it will go up to A, how much? N minus 1. No, sorry, just a minute. 0I, 1I, n minus 1I. So it will be n minus 1 comma 0. Plus, in B1 it will be a 0 comma 1 plus a, sorry, what would be here? 0 is there, so it is 1 comma 1 alpha plus a 2 comma 1 alpha square plus, it will be, sorry, it will be alpha power n minus 1 plus a alpha n minus 1 alpha power n minus 2 into beta. So in this way we will write, and what will be the last term here? Last term will be a b minus 1 thing. So it will be 0 comma b minus 1 plus a 1 comma d minus 1 alpha plus a 2 comma d minus 1 alpha square plus dot plus a n minus 1 d minus 1 alpha to the power n minus 1 beta t minus. That much. What does that mean? First answer there. That means actually I can write it as aij alpha to the power I beta power j, where all combinations will be there. So where I will be vary from 0 to n minus d is 0 to n minus 1, yeah, and j will vary from 0 to I think d minus 1. Fine. So that is the element of general element of the form. Okay, that is the general form of an element of this thing, of this thing. So if anybody asks you what is a general element of the form alpha 1, alpha 2, alpha 3, so it will be of the form aijk alpha 1 to the power I, b, alpha 2 to the power j, alpha 3 to the power k. Okay, where alpha k will be the degree of extension of sorry, alpha 1, alpha 2, alpha 3 over f alpha 1 and alpha 2. Okay, in this way you can inductively do this. So that means in f alpha beta okay, generally consists of if linear combination of powers and their products of alpha 1 alpha k up to a certain degree. What is the certain degree? Up to where I can take the polynomial alpha. So here alpha is taken up to n minus 1. So there is nothing alpha power n. Okay. So up to the algebraic, that depends on what I said about the algebraic extension, the degree of extension. That is the thing. Okay. For example, what is, suppose, q root 2 comma q root 3. How do you observe an element here? So by this theorem, I can say it is of the form a plus b root 2 plus c root 3 plus d root 2 into root 3 root 6, where a, b, c, d all belongs to Q. Understand? Why? Because here we'll conclude this. Why this is root 2, why degree of extension of this thing over Q root 2 is 2. I need to argue, okay? I will argue in the next example. So let me erase it for now. my point was that we know q square root of 3 over q is 2. But what is q root 2 is up to this, what is this? It is still 2 or not? Because I need this to compute this. I took there the beta on the degree of extension of beta over f alpha I2. So I need here this thing. So that I will argue. Okay. So first let us find out the degree of extension. So what is the degree of extension of Q? What is this? What is this? This is observed that this is actually because this thing is called already contained here. I sorry, this thing. If you this is 2 to the power 1 by 6. If you cube this, you will get this. So this thing will be absorbed here. So this thing is absorbed in this. So ultimately, the final result is this. For example, if I say that what is q comma 1 comma root, there is no right meaning of writing 1 here. That is simply q root. So similarly, here this thing I can produce by this. So and this is 6. Why the reason? Because the minimal polynomial of 6 root 2 over q that in x, that is x to the power 6 minus 2. So it is irreducible. Irreducible. Irreducible in Q. So let me write it properly. So that happened. Next example. What is this thing? What is this? Okay. So to answer this, let me write it in another ink. Okay. What is this? What is this? So this is for to find out this, we will make a tower of Field extensions. Is the proper tower here? So this thing I know is 2. I know that. I know that the extension of this is 2. Because the minimal polynomial is x square minus 2, which has no root in Q, or Eisenstein by you can say. This is 2. What is this? That is my question. If I can know this, actually this is equal to, then I can determine this by multiplying them. Okay. Now, We can do it in two ways, but I will mention both ways here. Okay. What happens? Okay. We know already also in q root 2 the equation x square minus 3 equal to 0 is satisfied by 3. Yes, because in q it is satisfied. So q root, the coefficients coming from q, so I can treat it as a coefficient of the q root 2 because q root 2 is already contains q, bigger set. So that extends degree of extension is base equals to 2. Degree of minimal polynomial. Okay. So if when it is equal to 1, when root 3 is there, or degree of minimal polynomial is 1. So if q root 2 is 1, then x square minus 3 equal to 0 at the of 4. My computer got hang. Further, what happened there? Okay, whatever is there. Further, it further splits in that means root 3 is present in q root 2. But it is impossible. Why it is impossible? Then root 3 can be written as a plus b root 2, where a b belongs to q and okay. Now if you square both sides, what I will get? Squaring both sides, I will get a square plus something 2b square plus then 2 root 2 ab equal to 3. That means I will get this relation. Fine. It is 2 root 2 ab. If now I will seek for a contradiction. If a b both are non-zero, then ab is non-zero because we are in a domain. That means I will write here. If AB is non-zero, both are non-zero, then AB is non-zero because we take AB from Q and Q is a domain. So we get root 2 equal to 1 by 2AB 3 minus a square minus 2b square, that thing, which is a contradiction. Why it is a contradiction? Because this number belongs to Q and root 2 belongs to R minus Q. It is irrational. So a rational number and irrational number becoming equal. So this is a contradiction. So that is the contradiction here. Now I need to show what happens if so A and B both cannot be non-zero. So either one of them should be 0. So if A equal to 0, B non-zero, then what is happening? Then what I can get from this equation? Then I can get 2b square equal to 3, which has no solution in Q, which is invalid in Q. Because in Q, we are multiplying a number by 2 and it is coming out to be odd number. But I mean, not this, it is not integer, but we can argue as follows that then b square equal to 3 by 2 and b will be plus minus root 3 by 2 type something, which is impossible in Q. Because b we choose a rational number. Again, if A equal not equal to 0 and B equal to 0, then what we got? Then we are getting A square equal to 3, which is again invalid. A equal to root 3. Because we took A from Q. Thus the only possibility is what is the only possibility? The only possibility is A and B both are 0. I mean A comma B comma A. So it's again a contradiction. Why? Because then, I mean, if this is the case, then root 3 equal to 0. I am writing correctly. Let me see. Actually, you don't know to square. You don't need to square actually. You can also argue from this line directly. Okay. You can also argue from here. But it is fine. No problem here. The problem, I mean, you need to finally bring a contradiction, whatever you can. But it is again impossible as root 3 not equal to 0. So such AB cannot exist. So root 3 cannot be inside root 0. So our assumption, what we assume, is wrong. That assumption is wrong. So the minimal polynomial is this thing, and degree of extension cannot be 1. It is exactly equal to. So impossible, which implies that x square minus 3 equal to 0. I mean, x square equal to 3 serves as minimal polynomial of root 3 over, sorry, root 3 over q root 2. Also, hence the degree of extension is this is 2. So that means, what does it mean? That means what we are about to find out. This is now this is 2, and this we at the first we mentioned this is 2. This is 2. So ultimately 4 equals to 2 cross 2 and this. That is the answer. Huh. Another way you can try, another way to try. Directly from computation. Find out q root 2 comma q root 3 over q without using this thing is, what is a direct element is, so if you take x equal to this, that will be of the form a plus b root 2 plus c root 3 plus d root 6. That I wrote here. That comes from this thing. That comes from this thing. So up to 2, up to 1 we can write, because 2 is the minimal polynomial degree. So 1 less than minimal polynomial degree we could write. So the minimal polynomial is degree 2, so up to root 2 to the power 1 we can write. Root 3 to the power 1 we can write. And that linear combination, because that was alpha I, alpha to the power I, beta to the power j. But I is only 1 and j is only 1. So that means root 2 to the power 1 and root 3 to the power 1 is possible. And after this, and then you can write it as x minus a equal to this thing. Consequently, rationalize this thing. I mean, whatever you did in, suppose, x equal to a plus b root, then what x satisfies? X minus a whole square equal to 2b square. I mean, then all entries are except x. X is invariable there. Okay, so after this, everything is rational and find the minimal polynomial. But that is very critical, difficult process and very lengthy process. Analyze increasing. Okay, but in this process, that is the utility of this process. In this process, we don't need the minimal polynomial of this thing, the big thing. This is very lengthy. We can avoid this thing in this process. Okay. Just a bit. Okay. This is fine. I think this is fine. And so let me proceed after this. So our next thing, we did a lot of study with algebraic extension and which algebraic extension and finitely generated an extension which is finitely generated and also finite extension. Everything we studied there. So is there any link between them? Is there any link connecting an algebraic extension, a finitely generated extension, and it is a finite extension? So in other words, can we characterize all algebraic extension of a field? All classes of algebraic extension, not a particular. All classes of algebraic extension of a field. That is my question. So characterize the type of algebraic extension. So that is our next theorem. The answer is yes. Why the answer is yes? We will answer in our next theorem. Actually, what happens, let me tell you first. So it is a finite extension if K is finitely generated and each alpha I are algebraic. That means it is K is algebraic, 1 minute. K is algebraic over F if K is generated by finite number of algebraic elements. Then the extension is finite extension. Sorry, it is finite. This is finite extension. So can we characterize a finite extension of a field or not? So it is finite if it is finite extension. Sorry. It is finite if and only if K is generated by finite number of algebraic elements. So finite extension means that thing. Let K over F be a field extension, then K is finite extension. Finite extension means what? It is finite dimensional as a vector space over the base field F. So it is finite extension if K equal to F alpha 1 alpha n where each of alpha I is algebraic In the other words, K is obtained by adjoining a finite number of algebraic elements. Over F. Okay. So, see, one part we have done here in the discussion. What is the discussion? In that discussion, what we have discussed earlier, one part is done. The converse part. If K equal to F an, then what is K colon F? We have shown that it is less than equal to n1, n2, nk. This is finite. And if they are algebraic, this is finite. I mean, this is less than infinity. So this part is I have discussed here. Yes, this part. This is finite. This thing. That means they're algebraic. Okay. Finite. There is simple extension is finite even if and only if algebraic. That we have also done previously. That we have also done previously. So we have to only show the converse statement here. I mean, if it is finitely generated, then every alpha is algebraic. So it is again a consequence of Tower laws. Converse part. Okay, I will write it later. So let me put the front part, the forward part here. So this is finite extension. Okay. So it is a finite extension. Finite extension means what? Then suppose so finite means it's a finite dimensional vector space over it. So suppose alpha 1 to alpha n. Suppose it is alpha n. That I mean that is some alpha 1 to alpha n. Okay. That is not, this need not be always a unique thing, but some exist. So I could have choose any basis here because the bases are not always unique. So I could have choose any beta 1 to beta m, but they have same cardinality. But okay, with I mean abuse of notation, we can choose this. Then suppose this is a basis of K as a vector space over the base field F. Again, I will use Tower law here. Just a minute. This is F. Take any alpha I. Okay. Now alpha F of alpha I is a subfield of K, and we can consider also F alpha I as a K subspace over F, because it is subset. First of all, it is subset of K. Sorry. Suppose first of all it is subset of K, and we can think this is a vector space over F. Why? Because it will satisfy the vector space axiom. Okay. Now, so this thing, will divide K colon F by the consequence of Tower law. This thing will divide K colon F for sure. Because why? Why it is happening? That is the thing. Actually, K colon F, I can write it as say, no. This thing is alpha n colon F alpha alpha I. Alpha is the intermediate subfield, and or I can also consider the tower thing. There is no harm. That is the thing. So that means alpha is content here. Okay, alpha is here. I take all alpha is. So this element is also there. So this is a, I mean, vector space over F alpha I also. So this is finite. So this and this both are finite, and this is this term into something is this. So that will divide this. Which implies K colon F is divisible by F AI colon F. But I mean, that is divisible means that is finite. What I said here, that is a finite extension. But we know already that a simple extension is finite if and only if alpha is algebraic. But this implies algebraic over. Okay. So there is arbitrary, as alpha I is arbitrarily chosen plus all those this set, all alpha is. So what we got? We got the first containment. I mean, or first condition. Proof of first condition. If it is generated by basis, then each of these is algebraic over F. and the converse is proved earlier. Okay. So next is an important corollary. Is the corollary. So we know that from ring theory perspective or from group theory, suppose kernel, you are defining a group adding for example from R to S phi, then kernel of phi is an ideal of R. Okay. In case of group, it is in case of group theory, kernel is subgroup of the original group. Again, image is uh, subgroup of that group of the codomain group. So, is there anything algebraic thing? Can I say in a field? In a field, there is nothing ideal because in a field, the ideals are 0 and 1. Okay, I mean the whole field, either 0 or it will be the whole field. There are two ideals. So, in a field, can the algebraic elements from a subfield? I mean, what I am trying to say that suppose alpha and beta be two algebraic elements, then subfield means everything I can do. I mean, in doing inverse plus everything. Then alpha plus minus beta and alpha by beta. Okay. Now I am going to estimate and alpha by beta if beta non-zero all belongs to all belong to F. So to prove this theorem, we will take help from this corollary, from above discussion, because all are algebraic over F. Sorry, the algebraic element forms a closed subset under the field operation. What I am trying to say. So one approach is algebraic means it satisfies some equation in F, coefficients in F. I mean in Fx, the coefficient polynomial in Fx and the coefficients are in F. But in case of if I want to suppose alpha plus beta belongs to is algebraic, then I need to find an equation in Fx having root alpha plus beta. But that is the construction is might be difficult, very difficult. I have given an equation that has a root alpha, I have given an equation that has a root beta. But alpha plus beta, what is the appropriate equation? I mean, that is a length-worthy term. So therefore I need to use that corollary of these things, that thing. Because that construction avoids, I mean, the above things. What I've discussed. This, actually not this. Okay, I will write it. Observe that each of the elements alpha plus minus beta, alpha beta, alpha by beta, obviously when beta non-zero, lies in f alpha beta, because f alpha beta is, I mean, quotient of two polynomials in alpha and beta. Okay, so they all lies in there, but alpha and beta are algebraic. I have assumed this. Therefore, that extension I mean, this is, what is this? Algebraic means finite. So we are done. So, aste aste. So this is finite. I have in for more clarification, I can add one thing. This finite extension and finite extensions in as algebraic. So it's algebraic. So algebraic means every element of this thing will satisfy some monic polynomial. I don't know what is the monic polynomial. Some polynomial. Monic is not needed in field case. So some polynomial. I don't know the polynomial here, but it will guarantee there are some polynomial I needed. They don't want what is the polynomial. They want whether it is algebraic or not. So it is an algebraic extension, and each of them lies in there. So that will this element will satisfy some equation there. That is that what we want. This will satisfy some equation. So we are done. Okay. Actually, I can say more. In general, if we impose the same multiplication and addition structure in, for a finite field for any arbitrary extension, suppose this k over f, arbitrary, I don't know what is the extension. It is finite extension or finitely generated or transcendental, I don't know. The set or, or algebraic elements form a subfield. Subfield of k. So in whenever you are looking at algebraic extension, algebraic elements, you don't need to look at all the to all the field. You need to look at only the algebraic extension. So in general, so it is the general statement here. Okay. Okay. So let me start. Now I have a question to you. The question is that now you are comfortable with the algebraic extension. So if I so let me Ask the question first. Is Q closer the elements of algebraic elements of C, which are algebraic over Q, is finite extension of Q. So that is natural to ask, and the answer is no. Right? Because take nth root of 2. It is satisfies the what, sorry, the equation x to the power n minus 2 equal to 0 in Q, in Qx, and in Qx, and it is irreducible. So it belongs to Q closer. Now, if I take some much more bigger n, that is n plus, sorry, that is n plus 1 through 2 of this, then, okay, so it implies that the degree of extension actually. Because why it is greater than equal to n? Because, okay, because Q adjoint this thing is a of Q closer, and this thing by the Tower law. By Tower law, so that divides this thing. So it is n. So it must be greater than equal to n, at least n. But if I take n is sufficiently large and n tends to infinity, then the degree of extension is tends to infinity. So it is never finite. Then the extension becomes infinite. So I mean, if it is less than m, I mean, if it is less than n, the degree of extension is uh, less than m, then there are m, at most m basis, dimension is m, so there are, in the basis, any basis, will be, over this extension, there will be m linearly independent element at most. But consider the equation m plus 1, m plus 1. This gives you root 2 square, sorry, it is m plus 1. It is m plus 1. So it will give you m plus 1 thing. So this is a contradiction, because basis says there are at most m thing, and I am getting m plus 1 number of a linearly independent thing. So it is impossible. But it is countable. Now, how we obtained Q closure? First, how we obtain Q closure? First, we note down all. So suppose n degree polynomial. So write all n degree polynomial. So there is an n degree polynomial, there is some n degree, there is n degree, n degree. So an n degree polynomial is determined by the coefficient. Suppose the n degree polynomial is x to the power n plus a0 equal to 0. So I can associate a tuple a n minus 1 a0. Okay, that belongs to q power n. So the n degree polynomial, the family of n degree polynomial, is countable union, because it is, I mean, it is countable. It is countable because it is represented by this thing, and this set is countable because q is countable. So countable product of countable set is countable. It is countable. So the roots of n degree polynomial, suppose there are n roots. At most there are n roots. At most there are also n roots. There are also n roots. So the number of roots of equations, it is also countable. Now I vary n. I vary n over n. Then I am getting countable union of countable thing. Again countable. Okay. That is the reason. Okay. That is the reason why it is countable or uncountable. Okay, so it is, do it as your own assignment. It uses the countability of q and n. Countability of q. Yeah, I'm again explaining. Just listen. So q bar is obtained from solving different degree equation. Suppose I first come to 1 degree equation. How many degrees are possible? It is ax plus b form, where a, b, how many equations are possible? Belongs to q. But this equation can be written corresponds to a comma b. Okay. So the number of such equation is countable. The number of such equation of degree 1 is countable because the parent set is q cross q. I am taking ab from q cross q. Q cross q is countable. So a comma b is countable because it is subset of a countable set. Okay. So, but a comma b corresponds to ax plus b. So number of such equation is countable. Now such equation give me one root. Okay. It's degree 1 root. So the number of roots from countable collection of this thing is countable. You can think as of n. So it is countable. Now second degree. What is the natural form? Ax square plus bx plus c. Now again this corresponds to every equation corresponds to a comma b comma c. Suppose the example is this. So this corresponds to 1 comma 5 comma 6. Okay. So second degree equation, that thing, this is countable set. A comma b comma c is coming from q cross q cross q. Cartesian product of countable is countable. So this thing is subset, this is countable. But this equation, every equation gives you 2 root at most. At most 2 root. So with each countable, with each tuple, there are only 2 possibilities. So at most. So either it will be alpha or it will be beta. So if the cardinality is x, there are obviously 2 into this type of thing, which is countable. Okay. Now for degree 3, for degree n, general degree n, there is a n x power n plus a n minus 1 x power n minus 1 plus a 0. So I can associate this to this thing. This thing is subset of q power n plus 1. Okay. This is countable. So the number of algebraic such equation is countable. So I can make countable number of this equation, and each equation gives me n roots at most n roots. So the total number of degree n equation is countable. Okay. This is if all of them gives exactly n roots, then it is n into the cardinality. It is countable, so this is countable. So now, what is Q closure? Q closure is union of this thing. How many I am getting from here? Suppose I am getting a countable thing. Union degree 2, or how many algebraic integer I am getting from solution I am getting from this thing. Again, this thing and this thing are both countable, so union is countable. Now how many I am getting from n? Take the countable union, then it is become countable. So gradually I am doing union of countable thing. So it is countable. Okay. So you understand? Next thing is the last theorem of the video, which says that algebraic extension over algebraic is algebraic. That means if I have an extension k over f, and if L over k, if both of them are algebraic, so I can write it there. If k comma f, if both of the extensions A comma F and A over K are algebraic, then the extension L over F also algebraic. That I need to solve. So the tower is this thing. I mean, here top field is L, it is K, it is if I draw it perfectly, it will be a line to draw it. If this is sorry, the top tower is L, this is L, this is K, this is L. If this is algebraic, suppose this is algebraic and this is algebraic, then this also is algebraic. So we pick an element and so this satisfies. Okay. So we will do in the following way. Suppose pick alpha, then alpha will satisfy some equation and consequently we will use the tower law. Okay. Tower law to see that alpha is algebraic. So we will not, again, we will not use write the minimal polynomial of alpha over this thing because we don't know what is this. Okay, let me write. Let alpha belongs to L be arbitrary. This also extension. So alpha L over K is algebraic. So there exists an equation such that alpha is a root. Okay. Let the equation, so I am writing let x to the power n, a polynomial, sorry. Polynomial, let me write in where there exists a polynomial in kx, because I am using the fact L over K is algebraic. So if I take any element, I will get automatically an equation by the definition of algebraic equation. Let of the polynomial. A0. That is the equation. Is satisfied by alpha. Then obviously these things. Sorry, it is alpha. Okay. Exactly where a n minus 1, that must be from the k, because I am using the fact that L over k is algebraic. Now I will use Tower law. Okay. Consider the field extension of f. What is the field extension? F alpha and coefficients. Consider this thing. This is an extension, right? So this is an extension. So this is an extension. Now I will use the use of Tower law here. How to use? We have this thing. This colon f. What is this? This is actually I am breaking into two towers. A n A0. What if but alpha 0 to alpha n, these are from k, and k over f is algebraic. So this extension, sorry, this extension is finite extension. Why? Because by the previous theorem. So I am adjoining some algebraic element with a field. They are algebraic element because k over f is algebraic, and this element belongs to k, and it is algebraic. So it is algebraic extension attaching finite number of algebraic elements. So by the previous theorem, this is algebraic. This is finite. Sorry, this is finite extension. Also this thing. is less than n, because I already got an n degree polynomial. Because I already got that polynomial, and that polynomial is from if a0 a1 over x. So if this is minimal, the extension of the degree is n, but I don't know it is minimal or not. Minimal means if it is not minimal, then degree will drop. But as I don't know, so it is less equals to for minimality. So it is again finite. So both of them are this is finite. So this extension is finite because it is product of two finite numbers. Thus, that extension is finite. But we know that finite extensions are algebraic extensions. Hence, uh, it is finite. Hence, f over this thing is finite. Algebraic extension. Okay, so it is finite but algebraic extension. So, but alpha belongs to here. It is algebraic, so alpha is algebraic over f. But alpha belongs to this. Alpha belongs to so alpha is algebraic. So this is the thing. So I took any element from L and so this is algebraic over f. Huh. Okay. So I need to mention that so Q closure is not R or C because it is infinite. The cardinality is uncountable, but it is countable. Okay. So it is a proper extension. Proper extension of Q, and that is properly contained in C or R. Okay. So you might see that example is this is Q crossover over Q is algebraic but not finite extension. Finite extension is algebraic. The converse is not true. When the converse is true in this case. Finite if and only finitely generated by algebraic elements. Okay. So I will to conclude the class here. Thank you.